My name is Liang He. I'm currently a faculty at University of Colorado, Denver. So today I'm presenting our work recently on diagnosed vehicle systems using batteries. So this is a collaborative work from, of course, UC Denver, and also UT Dallas, Microsoft, and also Shanghai Jiao Tong University. So let me start from this thing. Okay, I believe all you know this Boeing's accident, very unfortunate. So we have two of the crashes in less than 5 months, and with more than 300 people killed. And then all these Boeing aircraft are still grounded right now, so it has been over 7 months. And the good thing, relatively the good thing, is we know over these 7 months the reason why this thing happened. It's because on this Boeing, actually all the aircraft, we do have a type of sensor called angle of attack, AOA for short. And in this particular two crashes, this kind of sensor got broken, delivering the erroneous sensory data to the system. So let's see why we need AOA for aircraft. So AOA actually, by definition, is just the angle between the body of the airplane to the oncoming wind. Okay, as shown in the figure, this is just alpha here. And why we need this one? If we want to keep the aircraft in the air, we need a force, lifting force, right? And this alpha actually here is directly dominating how much a force we can have. Very straightforward. If the alpha is too small, we do not have enough force. But on the other hand, the important here is if we have a too large alpha, we still don't have enough or maybe very reliable lifting force to keep the airplane in the air, right? So this is the area called stall area. And we need to avoid that. And on this Boeing 737, they have a control system or a control module. It's called MCAS. This control module will take input of this AOA sensor to see, hey, if the alpha is too large or not. And if it's too large, it will do something to take the nose of the aircraft going down. And he will be doing this by just imposing two forces, one to the head of the aircraft and the other to the end. And one to the up direction, the other to down the direction. Okay, so this is normal case. But here we know in these two crashes, in these two accidents, unfortunately, this kind of AOA sensor goes wrong. Okay, and that will cause some issue here. It's because the aircraft could be just flying normally. But because of this AOA sensor goes wrong, the control system of MCAS takes some wrong control decision or actuation. So unnecessarily impose these two forces and then make the airplane goes down, eventually leads to the crashes. So in summary, actually, in terms of the factors, the accident is quite straightforward. Just wrong sensing data causing the control system to make the wrong control decision or actuation. That's the essentials of this accident. So, okay, sensory data, if that goes wrong, and if the control system do not have a lot of fault, let's say, tolerance, then maybe we can make the wrong control decisions. That's true. That's not only for aircraft, that's for all the control systems. But in practice, actually, this thing happens a lot because the sensor data could be wrong because, let's say, for example, in this particular case, the sensor itself is not working reliably. Okay. And also, after we collect the data, even the raw sensory data is right. When we are doing the after collection, the analysis of computation, we need software support. And then a lot of errors happens here. As we can see, not on aircraft, but on vehicles. We have a huge amount of recalls of cars. Many of them are due to software bugs. Okay. And then the third case, this sensor data could go wrong in control system is, okay, we have those cyber vulnerabilities. So if we have cyber attacks, then let's say a lot of security researchers on vehicle systems, they said, okay, the cars have digital part, have cyber part. And if the attacker can hack into the system and do something bad. And we do have, let's say, research project demonstrated one. The first one is a Jeep got controlled remotely when driving on the highway. And the second one is just any RPM, any speed showing on the panel of the car can be controlled, can be changed to any number. Okay? So actually, this is motivation, and we are trying to solve this or maybe help to solve this problem using a very basic idea called cross-validation. So let me show you some example. So let's think about, we are talking about cross-validation, and here we're talking about two sensors. One is the battery voltage of a car, and the other is the RPM. Information, in some cases, could be changed to any number by the habit. Okay, we have a car, and of course we have the engine. And this alternator will generate power. A larger RPM, we will have more power generated by the alternator. And then once the power is generated by the alternator, the power will go through two directions. The first one is, of course, like when we are driving, we turn on air conditioning, we turn on the light. Okay, that's power consumption part. And if we do have, let's say, remaining part of the generated power, this power could be used to charge the battery during driving. And if we are charging a battery with a larger power, in the ideal case, in just the pure physics or chemistry, we will have a larger battery voltage. Okay, so in this case, if we start from the engine end up to the battery voltage, again, we can see if we have a larger RPM or we drive the car faster, then in the ideal case, theoretically, we should have a higher battery voltage. And this uncovers an opportunity that maybe we can say something about RPM anomalies based on the battery voltage. And actually, this using battery voltage to do this kind of anomaly detection has its advantage because three things. The first one, all this here, the correlation or the dependency is based on something physical or mechanical. That means it's reliable and general for all the cars. And number two, this vehicle voltage can be directly collected. We just add a voltage sensor to the battery. And then number three, when we're collecting this voltage, we don't need to go through all the in-vehicle network, all the cyber components of the car. So it's kind of a more resistant to cyber vulnerabilities. So that's the motivation, and let's check if that's the case in practice. So we drive a car, a Subaru car, and so during the driving, we collect the RPM, we collect the battery voltage. And according to our previous, let's say, model-based analysis, we should be able to see, okay, when the RPM is larger, we should get higher battery voltage. But if we directly plot a scatter plot here, okay, things are not quite as expected. Okay, so that's the challenge, and then we can do something else. We can do more. Based on the raw data, we can do some data analysis, data mining, or maybe whatever the term. But anyway, after this processing, we have a very neat and clean linear model of the voltage and RPM. And the key here is it's not a one-to-one mapping between the absolute value of voltage and RPM, but it's kind of abstracted representation of these two information. The physical meaning showing here is actually when we are driving, we find a peak or a maximum local maximum value of the battery voltage. Then if the thing is in the correct way, we should be able to observe a peak in the RPM as well. Okay. So that's the observation, and then based on this observation, we design let's say, a kind of algorithm or anomaly detection algorithm. Essentially, it's a learning-based. So we take the voltage as input, and then we also monitor the real-time RPM, and then according to the algorithm design, we will output a conclusion to say, hey, if anything happened wrong in the RPM. And then the good thing is this. Cars are composed of or consist of a lot of interconnected physical components. That means RPM inside the car is not independent to everything else. It actually is quite correlated. It's strongly dependent to many other information there. So example here is, let's say when we are accelerating, we will change the pedal position, right? And then we will have throttle positions, so we can have more fuel injected to the engine. And then the engine RPM will increase, alternator power will increase, and battery voltage will increase. So a lot of dependency there in terms of the sensory data. So that means if we have voltage to RPM, we have a mapping, then very likely we will have a mapping from voltage to many other different vehicle information. And here we list, according to our results so far, there's 22 vehicle operation parameters or variables. We can identify some kind of relationship between these things and the battery voltage. And then we can construct a graph-based model to abstract these vehicles into a cyberspace using as a digital twin. And this graph will help us in doing this, let's say, real-time anomaly detection. So implementation. So we designed this thing, we implemented. Essentially, finally this prototype will be installed, it was installed onto the car battery. And it will monitor the voltage and at the same time collecting the vehicle information from the OBD2. And then it runs the algorithm and let us know if anything was wrong there. And then we install this one onto, beside the super previously mentioned, on 3 other vehicles to test the performance. And there is one actually major limitation for this kind of thing is we have the prototype. We can collect data. We can do the real-time anomaly detection. But the challenge is we don't have abnormal cases, okay, to safely collect the anomalies of the vehicle. That's the limitation. So what we have done is, okay, start from the very simple one, the trace-driven one. We have the normal trace. Actually, we have collected over 7,000 of driving traces, but all of them are normal ones. But anyway, we can insert those kind of anomaly traces there and to see, hey, if after this one we can detect these noises. And from the residue figure here, you can see if everything is normal, then the residue will increase gradually in a linear way. And if there's an anomaly, it will, of course, the slope of the increasing will change, and also it may not necessarily be linear anymore. So that's the first preliminary evaluation. And then we also did something hardware in the loop evaluation. So essentially here the trick is we are interested, let's say here in engine RPM, but we don't have the anomaly ones, abnormal ones. What we did is, okay, we install a RPM sensor to the view. So we can collect the view RPM. And this view RPM will be highly correlated, highly dependent to this engine RPM, but they are different. So in this way, this view RPM could be used as a promising candidate to emulate this kind of anomalies of engine RPM. And again, we can see, so the slope of the increasing of the residue changed due to the anomaly. And in the third part, it's kind of a real faulty information, okay? It's not because the RPM sensor is faulty, but it's because we managed to find a OBD2 adapter. That adapter is faulty. And this BDOG, our design, this prototype, will use that adapter to collect the RPM information. So anyway, so because the adapter is not reliable, it's not reliable. So that's a wrong data. And then again, we use this one to see if we can detect something goes wrong here. Yes. As a quick summary, we are talking about cars. Connected the physical component. And also, nowadays, the cars a lot of components are digitalized. So we have a lot of cyber components there. And this cyber component, we use the battery as a power supply. But on the other hand, if you look at it from another direction, because of this physical interacted component of the car, the cyber information, sensor data, you have a lot of strong correlation there. And then if we can identify those correlations, then we can collect them in real time and build up data-driven models to say if anything wrong in the car. Yeah. So thank you. That's the brief thing.
Our speaker first.